So this came from the 2010 AB exam. This was a calculator aloud question. This would have been the first free response question the students saw in 2010. So it says, there is no snow on Janet's driveway when snow begins to fall at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate. So the minute I see the word rate, I'm thinking velocity. Modeled by the function f of t equals 7t e cosine t. It's in cubic feet per hour. So again, rate in per hour, where t is measured in hours from midnight. So midnight represents time 0. Janet goes out to remove the snow at 6 a.m. The rate, g of t, in cubic feet per hour is the rate at which Janet removes the snow. So this represents her removing the snow. So from midnight to 6 a.m., she didn't remove any snow at all because she was sleeping. From 6 a.m. to 7 a.m., she removed 125 cubic feet per hour. And from 7 a.m. to 9 a.m., she removed 108 cubic feet per hour. And then it says how many cubic feet of snow have accumulated on the driveway by 6 a.m. So if you're trying to look at cubic feet of snow accumulated, are we looking at an integral or a derivative? An integral, good. So if I'm looking at accumulation, we're talking the area under the curve. So we would want to do from 0 to 6, the rate at which the snow is falling, which is f of t dt. So again, this is a calculator question. So you could simply write that integral down. That would have earned you 1 point on the AP exam. Your second point would be earned by getting the correct answer. So you'd hit math, go to option number 9, type 0, 6, type in that function. And hit enter. And we get approximately 142.274. If the original was, if the function we were integrating was in terms of cubic feet per hour, what would this answer be in terms of then? Good. Cubic feet. Then it says find the rate of change of the volume of the snow on the driveway by 8 a.m. So rate of change of volume of snow on the driveway by 8 a.m. would be the amount of snow fallen, and then the amount of snow removed. Now we're not looking for how much snow is there, but the rate of change of snow. So if you're looking for rate of change, we're talking about f of 8 minus g of 8. Because f and g represents rates. So f is the function inside the integral. So to find f of 8, you would do 7 times 8 e to the cosine of 8. I would just then hit subtract, so it keeps all the decimals. And g of 8 is going to come from our table up here. So g of 8 is 108. So you're just going to subtract 108 from that. And we get that the rate of change is negative 59.58. And you could write 29, you could write 3, and you could write 2. So they would have taken any and all of those decimal places. You could have had 0.582, 0.5829, and 0.583. And if we want to incorporate units, this is negative 59.5829 feet cubed per hour. So what that means is that the snow is being removed at negative 59.5829 cubic feet per hour. Let h of t represent the total amount of snow. Well, if h of t represents the total amount of snow, then h of t is going to represent integrals of g and f, because we're talking about in cubic feet, so we're working backwards again. Let h of t represent the total amount of snow that Janet has removed from the driveway at t hours after midnight. Express h of t as a piecewise defined function with domain 0 to 9. So h of t needs to be a piecewise because g of t is a piecewise, and we're going from the rate at which she's removing it to the amount of snow there. So the easiest one is to set this up so that you have 0 to 6. And the integral from 0 to 6 would be 0 to t of 0. And it doesn't matter what variable you pick. You could say ds, dt, etc. And we know that no matter what we integrate, did she remove any snow at hour 0? No. So this integral is actually always going to equal 0. So you could also have simply said h of t is 0 from 0 to 6. And then we could talk about from 6 to 7. And from 6 to 7, she is removing 125. So if you antiderive 125, you'd get 125, and then it's the top minus the bottom, so it would be t minus 6. And then the last part would be 7 to t, because because again, you don't know what time she's going to stop. This time it's 108. So it would be 108, t minus 7. And that would be through 9. At hour 6 and hour 7, we have to decide which part of the piecewise includes the 6 and the 7. We have to decide which one it includes. So here, at the 6th hour, she's still removing 0 snow. So it's actually the opposite of the way it's included here. At 0, the 6 is going to be included here. From here, we are beginning at 6 and ending at 7. And here we're ending at 9. And then the last part, how many cubic feet of snow are on the driveway at 9 a.m.? So now you need to find the integral from 0 to 9 of f of t dt and subtract from it the amount of snow removed. So snow is removed from 6 to 7. And it's removed from 7 to 9. And it's removed from 6 to 7 and 7 to 9 at different rates. So I would use my calculator. I'd just arrow back up. And I would select the 0 to 6 I already typed. And I would go over, instead of having to retype it, and change that 6 to a 9. And you get 367.3346 minus, we just said 6 to 7 is represented by this function here. So that'd be 125, 7 minus 6, minus 108, 9 minus 7, so again, on your calculator, since it's a calculator question, you could do minus 125, 7 minus 6 is 1, so I don't need to multiply. And then do minus, and that would be 108 times 2. So we get that there is 26.3346 cubic feet of snow on the driveway at 9 a.m. So at 9 a.m., there is 26.3346 cubic feet of snow on the driveway. Is everybody kind of feeling comfortable? They're okay with that? You can see the breakdown of the integration, why it's 6 to 7 and 7 to 9. This is the rate the snow is being added. This is the rate the snow is being removed. You need 2 integrals because the snow is being removed at 2 different rates. And again, it also makes sense to us that the rates are linear functions because if they're being removed at a constant, the antiderivative of a constant is linear. Therefore, area under the curve is sort of a rectangle. Okay. So what we're going to do today is extend that idea and concept of area under a curve. We're going to extend it to a looking at area between 2 curves. So over the past course of the few weeks, we've looked at area under a curve. Today what we're going to do is look at the area between 2 curves. So what we have to do is take into the account of the area under the top curve the area under the bottom curve. And if you want to get the area between them, it would be the total area under the top minus the area under the bottom. So it's kind of like the geometry questions we used to have in the day, where you had the square, and then like within the square you had a circle, and like the edges were shaded in. And in order to find out what the area of the shaded region was, you had to find the area of the square and the area of the circle, and then you subtracted the square and the circle to get the area of the shaded. So that's kind of what we're doing in calculus now. We want to find the area between two curves. So in order to find that area between them, we're going to take the area under the top, subtract the area under the bottom, and give us the area between. So the area between two curves is represented by this equation here. Area from A to B of f of x minus g of x. So oftentimes when we're talking about the area between two curves, you are going to hear me say top minus bottom. You're just going to hear me say it. It's the natural way to think of it. So let's actually investigate and look at some examples. So we have find the area of a region between two curves. We have y equals x squared plus 2. So what I'm going to do is graph that first region. So x squared plus 2 is a quadratic function shifted up 2 units. So that means it has a vertex at 0, 2. It is the point 1, 3. And again, we only want to find the area of the shaded region from 0 to 1. So we're looking for the area of 0 to 1. And it's going to be our top curve. So currently we have a quadratic that's x squared plus 2. The linear curve is negative x. So at 0, negative x is at 0. At 1, negative x is at negative 1. So that other curve is down here. So we can see that the top curve is blue. The bottom curve is red. So the area of the region bounded by blue and red would be this space right here in purple. So the integral from 0 to 1 would be the top, which is quadratic. So that's x squared plus 2 minus the bottom, which is negative x. And we're integrating with respect to dx. So once you kind of figure out your top minus bottom, this is now just a simple integral that we know how to integrate. We're integrating a quadratic function. So minus a minus turns to a positive. The antiderivative of x squared is x cubed divided by 3. The antiderivative of 2 is 2x. And the antiderivative of x is x squared over 2. And we're evaluating from 1 to 0. So you have 1 cubed over 3 plus 2 times 1 plus 1 squared over 2 minus 0 minus 0 minus 0. So 2 plus a half plus a third is, a half could be considered 3/6. A third could be considered 2/6. So you could have 5/6. You could also write it as a improper. So 2 times 6 is 12. 12 plus 5 is 17. You could check this on a calculator. Now your calculator is going to have a little bit more difficulty. So y1 would be your x squared plus 2. y2 would be your negative x. You do second trace and you do your integral. We're going from 0 to 1. What you're going to notice is that your calculator does not account for the area below. So our calculators have flaws in the sense that they will only find the area from the curve above to the x-axis. So I don't want you to just go put this in your calculator. If you were in the graph mode, if you wanted to see it in the calculator, what you could do is hit math. You could go to 9. You could do 0 to 1. And then what you would have to do is bars, y bars function, y1, minus bars, y bars function, y2. And do exactly what we did algebraically, top curve minus bottom curve. And now you can see you get that 2.883 repeating. And it may not work, a fraction, it did. You get that 17/6. Calculator, hand. Okay, example number 2. A region lying between two intersecting graphs. So in the last example, they gave you a restricted bound. So in this example, they told you from 0 to 1. In this example here, what you'll notice is there is no bounds. I simply have two curves. So what you have to do is sketch the two curves. So we're going to start by sketching F. So I'm just going to start at -2 and sketch it to the right. So I have 2 minus x squared. So my first x squared is -2. So 2 minus -2 would be like 2 minus 4. So you get -2. So that first point is at -2, -2. If I plug in -1, -1 squared is 1. 2 minus 1 is negative. 2 minus 1 is positive 1. So we plot our point at -1, 1. And then we know that our vertex is at 0, 2, because the quadratic is open down like a frown. It's shifted 2 units up. We also know it's symmetric about that. So if that points down 1 and left 1, this points down 1 and right 1. And my other point is down 4 and right 2. So there's my f of x. G of x is equal to x. Well, x is linear. And all of the points are going to meet at the corners. So what we'll notice is that these two graphs have 2 points of intersection. They intersect at -2, -2. And they intersect at 1, 1. Those 2 points of intersection are going to act as my upper and lower bound. So we're going to find the area between these two curves. The top curve is in blue. The bottom curve is in red. So again, my integral or my area is equal to top minus bottom and then since I'm integrating with respect to variable x, my bounds are also going to be respecting to the intersections of variable x. So you're going to start at -2 and end at 1. Find your antiderivative. Antiderivative of 2 is 2x. Antiderivative of x squared is 1/3 x cubed. Antiderivative of x is 1/2 x squared. And you're evaluating from 1 to -2. So you have 2 minus 1/3 minus 1/2 minus, because it's f of b minus f of a. So I'm going to put that second part in a bracket. 2 times -2 minus -2 cubed is -8. -2 squared is +4. Since I have a third and a third and a half and a half, I'm going to distribute my negatives before I try to simplify these. So I have 2 minus 1/3 minus 1/2. -2 times 2 is -4, but distributing your negative, you get a +4. A -8 and a negative becomes a positive, but you distribute the negative. So you get -8/3, and you have 4 divided by 2, which is 2, and that's negative, but the negative makes it positive. -1/3 and -8/3 come together as -9/3. -9/3 would be like -3. 2 and 4 is 6, so 6 minus 3 is 3. 3 plus 2 is 5. 5 minus 1/2 is 4.5 or 9/2. Questions at all on the setup, the graph, and the solution? Okay, let's look at example number 3. This time we have some trig involved. So I've said how important it is to kind of know your trig, know your points of intersection, know your unit circle. So it says find the area of one of the regions bounded by the graphs of f of x equals sine x and g of x equals cosine x. So we know that the graph of sine starts at 0, 0. At 1/2 pi, sine is at 1. At pi, sine is back to 0. At 3 pi halves, sine is at -1. And at 2 pi, sine is back at 0. Which also means at -pi halves, sine is at -1. Cosine is a little different. Cosine starts at 1, goes to 0, goes down to -1, comes back up to 0, and finishes at 1. So what you'll notice is that there are a bunch of different regions that could be considered shaded and overlapped. It said find the area of one of the regions bounded by the graphs. So what I want you to notice is that you have a region here. So this could be represented by region 1. So what's in orange, their point of intersection would be right here. So if that's -5 halves, then their point of intersection would be -3 5/4. That should make sense that sine and cosine intersect at 3 5/4. If you think about the equation sine x and cosine x, sine x and cosine x are the same in quadrant 1. So they're the same when x is equal to 5/4. And they're also the same in quadrant 3, which is when x is equal to 5 5/4. And the same if you go backwards, which is -3 5/4. So this area in orange could be represented by the integral from -3 5/4 to +5 5/4, which would be this intersection here. The top curve is red. Red is cosine minus sine So be careful, don't fall into the trap that f of x is the first curve listed and is always the top curve. In this case, since I did the bound from -3 5/4 to 5/4, the top curve became cosine, which was the second curve listed. So the antiderivative of cosine is sine. The antiderivative of negative sine x is positive cosine x. And we're evaluating from 5/4 to -3 5/4. So you'd be subtracting the sine and cosine from the second part. Sine of 5/4 is √2/2. Cosine of 5/4 is √2/2. The sine of -3 5/4 is -√2/2 because that's in quadrant 3. So you get minus a minus, minus a minus, making them all positives. So you have 1, 2, 3, 4. So you get 4 square roots of 2/2, which becomes 2 square roots of 2. Alternatively, you could have found the area under the curve, and you could have started at 5/4 and gone this direction. You would have gotten the same area under the curve. It's just that now your top would have been sine and your bottom would be cosine. You can check that on a calculator if you want, but the area will be the same. Okay, the bell's going to ring in about a minute. I'm going to give you guys the same 4 minutes that the rest of your peers get. So when that bell rings, you can leave. When it rings again. You should be back in and ready to pick up. We're going to continue to look at area between the curves. The next thing we're going to look at is area between the curves with respect to y. So like I said in the last one, we were doing it with respect to dx. Now we're going to integrate with respect to dy. So we're going to look at how that changes our bounds and go on from there. Okay, you can take your break. Okay, so like I said, we are picking back up with the area between two curves with respect to y. So in the last few examples, we were differentiating with respect to dx. Now we're going to integrate and antiderive with respect to dy, which means instead of top minus bottom, we're going to be doing right minus left. So in the dx, it's top minus bottom. In terms of dy, it's right minus left. So example number 1 says find the area of the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. You have two ways you could go about finding the points of intersection. You could graph them and find the points of intersection on the graph. You could also, because both of these are x equals, you could go back to our algebra days and you could set the two equations equal to each other. So they would also intersect when 3 minus y squared equals y plus 1. So that's y squared plus y minus 2. So what that tells me is these two graphs will intersect when y equals negative 2 and y equals 1. And again, you could find those points. Now to graph these, you could graph them as x equals. You could also rearrange our terms again so that you could see these as y equals equations. So x equals y plus 1 is the equivalent of y equals x minus 1. And x equals 3 minus y squared. So that one would be a little trickier to solve for y because then you're going to end up with a plus or minus x. So what I do is I kind of just turn my paper and I say, okay, this is kind of like the x-axis now and this is kind of like the y-axis now. So if y was equal to 3 minus x squared, x equaling 3 minus y squared tells me I have a quadratic shifted up 3 units. So this is going to go through 3 on x, and it's open down. And I know that if I graph a quadratic, open down, it would look like that. So then I just take my paper and I turn it back this way, and I can see the two square roots. Here's the square root of x. Here's the negative square root of x. So again, I can see also, we said these graphs were going to intersect when y is equal to negative 2. Y is equal to negative 2. Boom, there's my intersection. It's at negative 1, negative 2. And here we said they were going to intersect at y equals 1. And they do, in fact, intersect at 2, 1. So right minus left is going to be blue minus red. So when you talk about the integrals for y, you're going to go from the lowest to the highest. So you're going to go from -2 to 1. Right, which was 3 minus y squared, minus left, which was y plus 1. And again, we're differentiating with respect to y. So this is equivalent to -2 to 1 of y squared. So you have negative y squared. You could group together your other terms. So you'd have -y, and this would be like 3 minus 1, which would be a +2. Take our antiderivative. So you have -y cubed over 3 minus y squared over 2 plus 2y, all being evaluated from 1 to -2. Make sure you watch your signs carefully. So -2 cubed is -8. -8 times -1 became +8/3. And I know we're going to also distribute that in. So again, I have -8/3 and -1/3. So that's going to give me a -9/3, which is really -3. And then I have -1/2. I have +2. A negative. So 4 divided by 2 is 2. A negative times a negative would give you a +2. And a negative times a negative will give you a +4. So 4 plus 2 plus 2 is 8. 8 minus 3 is 5. 5 minus 1/2 is 4.5. Looks a little familiar. So again, we have a very similar problem to the one we looked at before with x's, but now it's dx's. That graph was shifted up 2. This graph is shifted up 3 because the lower graph is shifted down 1. Okay, in example number 2, it says find the area bounded by the following curves. So curve number 1 is y squared minus 2. So that is going to be this blue curve here. As well as y equals -1. So that's the horizontal line here. So we have a point of intersection right here, as well as y equals 1. So that's this line here. So I have another point of intersection at -1. And then lastly, by the curve x equals e to the y. So really that's a natural log. And they intersect here and here. So we are finding this area in pink. So sometimes when you find the areas of curves, what you're going to notice is that right minus left, top minus bottom, They all play an important role. If you tried to do top minus bottom, oh holy moly, the top and the bottom would change consistently. Here, if you did top minus bottom, you would have to break this up here. So you had this top curve and this bottom curve. Then you would have to break it up and do this rectangle. Then you would have to break it up and do top here, bottom to there, and then top from here, and bottom there. You would have to have 1, 2, 3 integrals to do top minus bottom. However, if you do right minus left, the curve here on the right side is always red. The curve over here is always that blue curve. So the right curve is always e to the y. The left curve is always y squared minus 2. And the y's are bounded by -1 to 1. So the area between the two curves for the pink would be from -1 to 1 of e to the y minus y squared minus 2. And then what you're going to do is find all your antiderivatives of each of those terms individually. So the antiderivative of e to the y is e to the y. Antiderivative of y squared is 1/3 y cubed. And antiderivative of 2 is 2y. Evaluated from 1 to -1. So you have e to the 1 minus 1/3 plus 2 minus e to the -1. -1 cubed is -1 times -1 will be positive 1/3 minus 2. And then you'd have e to the 1 minus 1/3 plus 2 minus 1 over e minus 1/3 plus 2. So 2 plus 2 is 4. 4 minus 2/3 is 1 and 1/3, or sorry, 3 and 1/3, plus e minus 1 over e. Okay. And the last thing we're going to look at is what happens if a curve intersects at more than one point. So take a minute and graph each f and g on your own. Find your important key points and graph those functions. So as I work through graphing these key points on my own, what I like to do is always look for a GCF. I like to find my roots so that I can plot the zeros on the graph. It helps me kind of see points of intersection. It helps me kind of see the shape of the graph. So for both F and G, I took out their GCFs and I kind of found their roots. A second easy way to find the areas of the regions and sketch a graph is to set the two functions equal to each other. I know that if I'm finding the area between them, I know that they have to intersect. So you could say F equals G. So you'd have 3x cubed minus x squared minus 10x equals negative x squared plus 2x. So then I would move over my x squared as a positive x squared. Canceling my x squared terms, I'd subtract the 2x, so I get minus 12x equal to 0. Once again, I find that I have a factor or GCF of 3x. That leaves me with x squared minus 4. So that has me happy as well because x squared minus 4 is a difference of squares. So that tells me that these two graphs intersect at 0 as well as plus or minus 2. So then what you could do is plug in 0 and plus or minus 2 to either graph and find those key points. So I already know g of 0 is 0. G of negative 2 would be negative 2 squared plus 2 times negative 2. So negative 2 squared is positive 4. But then you get a negative 4 and then a negative 4. So we get negative 8. So if you look over at my graph, I had that point negative 2, negative 8 on my curve. I have the point 0, 0 on the curve in blue. And then I could also plug in g of 2. And I see that it's also a 0 or a root. And I knew that from up here and had that plotted as the point here. So that means f of x goes through all of those same points. It goes through 2, 0, it goes through 0, 0, and it goes through negative 2, 8, or negative 2, negative 8. So what I would need to do at that point is then kind of figure out, okay, what is f doing at something like negative 1, and what is f doing at 1, simply to help give me an idea of what that curve looks like. So 3 plus 1 is 4. 4 minus 10 is negative 6. Negative 6 times negative 1 is positive 6. So at negative 1, the graph of f is at 6. So I know my graph goes from here to there, back to here. And then I would want to know what's my graph doing at 1. So 3 minus 1 minus 10, well, 3 minus 11 is negative 8. Negative 8 times 1 is negative 8. So then that tells me my graph is coming back down and then going back up. The reason I needed to know what it was doing between those points of intersection would be to determine which graph is the top and which graph is the bottom. So this area between these two curves is going to get broken up into this region over here on the left. So that's area 1 plus area 2, where the top and bottom curve is changing. So the integral for area 1 is this point of intersection here at negative 2 to 0. The top curve is red, so that's f of x. minus the bottom curve, which was blue. And then what I'm going to do is add to that the area from 0 to the next point of intersection. But now the top curve is blue, which is G, minus the bottom curve, which is red in F. So if you have a graph that intersects at more than one point, the area, or the total area, is the area of one region plus the area of the other region. And then what we're going to do is integrate and find those areas. Yep. So it's all based on the graph. So it's top minus bottom, or right minus left. So for the orange area, the top graph is that red graph, which is represented by f of x. So for that first region, I know f comes first because f's on top. Does that help? And then like here, g is on top, so I list g first. That's if you're evaluating with respect to x. And then if you're evaluating with respect to y, then it would be right minus left. Now what would make right minus left really difficult for this function is that it's blue and red on the right. So this would be really, really, really difficult to evaluate with respect to y's. Okay, so I have two kind of lengthy integrals. You can clean them up. So what's really, really nice about this is you have negative x squared and positive x squared. So they're going to cancel. Here I have negative x squared and positive x squared, so they're going to cancel. So I'm evaluating the integral from negative 2 to 0 of 3x cubed minus 12x. And I'm evaluating the integral of positive 12x minus 3x cubed on the other side. So once you find your antiderivatives, again, you can clean them up. 12 divided by 2 is 6. Plug in your values for the upper and lower bounds. So plugging in 0, 0 to the fourth is 0, 0 squared is 0, so it doesn't mean a whole lot. It's helpful to write it, though, because it's upper minus lower, so you don't want to lose your negative. And then it would be 3, negative 2 to the fourth is a positive 16 over 4 minus negative 2 squared, which is 4 times 6, plus plugging in the top, so you have 6 times 2 squared, which is 4, minus 3/4 2 to the fourth, which is 16, and then this time minus 0. So that negative is going to distribute in. 16 divided by 4 is 4. 4 times 3, so you have negative 12. 6 times 4 is 24, but negative makes a positive 24. Positive 24. 16 divided by 4 is 4. 4 times 3 is negative 12. So 24 and 24 is 48. 48 minus 24 is 24. So what that means is the area of that orange and purple summed together is 24 units. Area of the orange and purple summed together is 24 units. So your homework is in your textbook. We are in lesson 7-2. The page numbers that go along with that, I'll be writing up on the board for you in just 1 second. So like I said, I kind of modified 7-2. I used to do it over 2 days. I pushed it into 1 to try to help us have more days to review. And the homework is on page 400. Nope, not quite. 395. And I have, so I want to modify it again just because I don't want to give you a double assignment. So I'm going to take half of each part from my previous years. So we're going to go to page 395. And we are going to look at 1 through 21, the odds. That should cover both. Let me make sure it covers the Y's as well as, yep. So that will give you a look at, actually do 1 to 19. 21's kind of brutal. Don't do 21. 1 to 19 odds. And on 13, make sure you split the tangent at 0. Yep. So I will be live tomorrow at 8:31 a.m. We are looking at lesson 7-3, which is the next set of notes in your packet that you have.